Hey guys, we're going to look at exponential functions today. So this will start a new unit looking at exponential functions. Today we'll kind of look at some of the features of those and be able to identify something as exponential. And then we'll start looking at how to apply exponential functions to some more realistic type situations using something called exponential growth and exponential decay, that kind of thing. But for today's lesson, we're going to just look at exponential functions as a whole and hopefully be able to, by the end of it, identify exponential functions to be able to, actually, let's say recognize. Exponential functions from tables, graphs, and equations. So you know that an exponent, while y'all are writing that, we'll just kind of talk about this. You don't have to write this part down. You know that an exponent is that little number that is above a base number that allows you to know how many times you're multiplying that number by itself, right? So if you have a number like 2 and you raise it to the first power, well, that equals 2. And 2 to the second power is the same thing as 2 times 2, or 4. And 2 to the third power is the same as 2 times 2 times 2, or 8. And 2 to the fourth power would be the same as 2 times 2 times 2 times 2, which is 16, and so on, right? So exponents allow things to multiply repeatedly to be able to create whatever new number you want to be able to create. So when we're looking at exponential functions, we're talking about functions or equations, right, that have a multiplication pattern associated with the points values that they have. So if you look at this, to go from 2 to 4 to 8 to 16, if we want to look at that pattern of numbers vertically here, there's a times 2 pattern in that, right? 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. That's the kind of thing that we're talking about when we're talking about exponential functions in algebra. So you already know about linear functions. We've learned about linear functions already. Linear functions are the ones that graph as a straight line, right? So when you look at function values on a linear function, you're going to notice that there's an addition or subtraction pattern. We're going to say adding. But there's an addition or subtraction pattern in the values of that. For example, in this graph over here, a point at 0 is located down here at -5. When I go to where the x is 1, I have a point located here at -2. When I go to where the x is 2, I have a point up here located at +1. When I go to where the x is 3, I have this point up here at 4, right? So if I look at the pattern in that table, I have a +3 pattern throughout. So to move up that line, up the function, we've got a +3 pattern going on. That's a linear function when we have that addition pattern in the table. You already know how to write the equation of a linear function as y equals 3x, because our addition pattern is 3, right? 3 divided by 1 would be 3. Minus 5, because our y-intercept is 5, based on where the x value is 0. So we've learned this. We already did this earlier in the year. You learned about this last year as 8th graders. We should be pretty familiar with linear functions. But one of the standards for algebra is being able to distinguish between linear and exponential. And then we got to be able to learn all the things we need to learn about exponential, but that's part of it. So in an exponential function, rather than increasing or decreasing by addition, we're now going to be increasing or decreasing by multiplying by a certain amount. And this could also go with dividing, because multiplying and dividing are inverses of each other. But if you're dividing by something, you're multiplying by its inverse. So same idea. So this graph represents an exponential function. So we no longer have a straight line. We now have this J-shaped curve. That's what you typically see in an exponential function. And so you'll notice that the values in that, if I go to fill in this function table over here, at 0, I have a point at 1. At 1, I have a point up here at 2. When my x is 2, my point's up here now at 4. When my x is 3, my point's all the way up here now at 8. And so we no longer have an addition pattern, because this would be like +1, +4. I'm sorry, +1, +2, +4. So not really an addition pattern in that. But there is a multiplication pattern here of times 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. That's what makes this exponential. So with the linear, we have that addition pattern. With exponential, we have this multiplication pattern going on. Exponential functions are things that involve increasing or decreasing by percentages, because that would be multiplication. Or if they say some number of times, that something is going to be happening, like it's doubling or tripling or quadrupling or whatever, that's going to be an exponential situation. The equation for an exponential function writes with the format of a times b to the x power. And we'll talk about that in a slide or two. But the equation for this one would be 1 times 2 to the x. So the 1 comes from the y-intercept, the place where it touches the y-axis. And then the 2 comes from what multiplication pattern we see in that. So we want to be able to recognize things as exponential from a table like this, if we can see a multiplication pattern in it, from a graph like this where we see that J-shaped curve, or from an equation that's set up like this where we have a number times a number raised to the x power. X will always be the exponent in your exponential function. So looking at all that, let's look at some examples of things we want to be able to identify from a table. So if you look at a function in a table and you want to recognize it as exponential, you want to look for things that grow by multiplying or dividing by the same amount as you work through it. Now, what's important is that you check your x's first, because you need to check between 2 points that are counting by the same value on the x. If your x is counting up by the same pattern, like this is 1, 2, 3, 4, 5, 6, then we can just check our y values and be good. When we get down into the slides a little bit further, we'll look at some that don't do that, and we'll have to pick specific points off the table to check. But as long as you can pick 2 points to check, you can usually figure out whether it's going to be exponential or linear between the two. So looking at this one, my x's are going up by the same amount, so let me check my y's and see how they're changing. Our decision is going to be based on how the y's are changing. We're not really worried about the x as long as they're consistently counting. But if I look at the y's, I go from -4 to -2 to 0 to 2 to 4 to 6. That's a +2 pattern. -4 plus 2 is -2. Plus 2 would make 0, plus 2 again would make 2, plus 2 again makes 4, plus 2 again makes 6. Since there's an addition pattern in this table, this is a linear table. But the one to the right, if we look at it, again, double check your x's to make sure they're consistent. 2, 4, 6, 8, 10, 12. That's fine. It's counting by 2s all the way through, so I don't have to worry about changing anything. I just need to be able to look at this part. And so I go from 1 to 4 to 16 to 64 to 256 to 1024. So it could be an addition pattern. 1 plus 3 is 4, but 4 plus 3 is not 16. So an addition pattern doesn't work here. But you can see a times 4 pattern. 1 times 4 is 4, 4 times 4 is 16, 16 times 4 is 64, and so on. So we have this multiplication pattern happening here. Since it's a multiplication pattern, that makes this exponential. Now, if you are not friends with multiplication, which is okay, happens that way sometimes, you always have the option, if you can't tell what they might be multiplying by, you can always divide. If you need to divide to check, divide a second y by a first y to be able to see what they would be multiplying by. So for this, I would do 4 divided by 1. Or you can go 16 and divide by 4. Or you can do 64 divided by 16. You just have to do 2 consecutive points and do the second one divided by the first one. So the bigger one is not necessarily the bigger one. The one that comes second has to go on top. And that would allow you to be able to see what it multiplied by to be able to change. On a graph, an exponential function is going to look like this J-shaped curve. Now, the curve can be increasing, it can be decreasing from the top, it can be increasing from the bottom. All those are options that you can see on a graph version of an exponential function. We're not going to really write anything on this slide. I just wanted you to get a picture of it. Something that you could see when a test on this rolls around is them give you 4 different graph options and ask you to choose the one that represents an exponential function. So you need to at least understand enough about the shapes of functions to be able to tell. Exponential are going to be these J-shaped curves. Anytime they want an exponential function, you want to pick one that looks like that. Okay, let's talk about the equation of one. So the equation we already said on the other slide is represented by a times b to the x. Now, you don't have to memorize that. That's on the formula sheet for your algebra test. So we just need to understand how to use it. Now, they're not going to tell you what the a, the b, and the x mean, but they will give you that format. So in that, remember that a is the y-intercept. B is the factor that you're multiplying by. And then x is always going to be the exponent. Now, in a exponential growth or decay problem, which is what we'll look at later, x is going to represent time. But in a normal exponential function, it may or may not, but it's always going to be the exponent. Now, here's something to think about. The b value is what determines whether your function is increasing or decreasing. So that's a number that you're multiplying by. If you think about multiplying, if I multiply by 1, everything stays the same. Don't write this down, by the way. Right? So if I had 2 and I multiplied it by 1, still going to get 2. Nothing's going to change. Not going to increase or decrease. If I multiply it by 3, I now have a 6. That got bigger. Went from 2 to a 6 when I multiplied it by 3. If I multiply it by a third, it becomes 2/3. Well, 2/3 is smaller than my original 2. So the rule for this, or the thing to think about with the b value, if you want to decide if your function is going to be increasing or decreasing, because it can go either way. If the b value is greater than 1, a number bigger than 1, the function will be increasing. And when the b value is between 0 and 1, the function is going to be decreasing. So if you're looking at, and again, you don't have to write this down, but if you're looking at an equation like 3 times 4 to the x, and they want to know if it would be exponentially increasing or exponentially decreasing, you can just look at this number in the middle, and if it's bigger than 1, it's increasing. If it's smaller than 1, it's decreasing. So 3 times 4 to the x would be an increasing function. 3 times 0.5 to the x would be a decreasing function. So you want to be able to keep that straight based on that. When we get into exponential growth and decay, that will make more sense because you'll be seeing that a little bit more. But just know that that b value is what determines whether it's increasing or decreasing. The a value is just where it starts. So let's look at some tables and see if we can decide if they are linear or exponential based on what we see. So again, with these, we want to look down the table on the y's to be able to see what it's changing by. Now, I'll tell you a good tell for this if you know it's going to either be linear or exponential and there's not like a neither option. If it goes from positive to suddenly negative, it can't possibly be exponential because you can't multiply by something to generate positive numbers that you can also multiply to generate negative numbers unless it goes back and forth. Like if you're multiplying by a negative, it'll flip-flop back and forth between the two. But if I would have to multiply by something positive to get from here to here, but then something negative to get from here to here, there's no way that that was done in this for it to be exponential. But you can also just look for the pattern. So if I'm looking at this from 7 to 4, is a decrease of 3, and I see that pattern stay consistent through here, where it's decreasing by 3 every time. That means this is linear. If I wanted to write the equation for that, I would have y equals negative 3x plus 1. This is what determines the b value on that, remember? And we can look at the same thing in a set of points like this, where I'm looking at the y values in my set of points. My points go negative 2, negative 1, 0, 1, 2. So I don't have to worry about what it's counting by on the x's. I'm just looking at the y's. And so I'm looking from 1.75 to 3.5 to 7 to 14 to 28. Now I'll tell you that it would make sense to me if you said, well, I don't know what 1.75, if I'm multiplying or if I'm adding to get from here to here. That's not really mental math. I'm not saying you can't do it in your head. But I'm saying that typically when we talk about like doing mental math in your head, that's probably not one of the calculations you typically would think of. But a lot of you guys probably, if you look at the end of the data, can recognize that to go from 7 to 14 would be times 2. And from 14 to 28 would be times 2. So you don't necessarily have to use the front part of the data to recognize the pattern that's in it if you can recognize it on the back. And then you could go back and double check from the front if you wanted to. 1.75 times 2 is 3.5. And 3.5 times 2 is 7. And we do have that multiplication pattern that holds all the way through. But if it's hard for you to identify it from the front, like if looking at these numbers doesn't help you to see times 2, but looking at these does, well, use whatever part of it works for you. It's fine to use the back half of the data instead of the front. Anyway, a times 2 pattern in this tells me it's exponential. Again, just for the sake of practicing with it, to write that equation, we would put our y-intercept, which is 7, that's this point right here, times what we're multiplying by, which is 2, to the x power. We'll do some more work with writing these things tomorrow. But if we can get a little bit of that figured out today, that would be good. Looking at the next table. Actually, take a minute with your, I don't know if you have people or not. You might be home by yourself. Anyway, take a minute, pause the video right here, and decide what you think the pattern in these tables shows as far as it being linear or exponential. And then if you feel comfortable, try to write an equation for it if you can. But make sure you pause the video and actually do it. Okay, hopefully you paused the video, and now we're back. Looking at this one, I would hope that you recognize that it was exponential with a times 6 pattern in it, right? Times 6, times 6. And again, you could see that here too with these. So the equation, if you were brave enough to write that, would be 2 times 6 to the x. Again, the 2 coming from the y-intercept, and then the 6 being what we see in the pattern. And then in that second one, hopefully you recognize that as linear. There was a plus 3 pattern in that. From -4 to -1 was plus 3. -1 to 2 is plus 3. 2 to 5 is plus 3, and so on. So the equation for that would have been 3x plus 2. Again, the y-intercept on that being at 2. We see that in there. So I need you to for sure be able to distinguish between the two. Whether you can write the equations yet or not is not a huge deal. We're going to work some more on that. But I need you to at least be able to look at the patterns in these things and be able to say, okay, that's adding, that's linear. Okay, that's multiplying, that's exponential. And be able to kind of move down through that. In addition to that, we also want to be able to describe things about exponential functions like domain and range, and then the intercepts of them. So if you remember back when we learned about functions, when we were doing our unit on linear and we were doing our unit on functions, we talked about how domain represents all the x values in the function and how range represents all the y values in the function. With an exponential function, don't draw this, but I just want you to think for a minute. If we graphed an exponential function on here, it would look something like this. And so what you see with an exponential function is the idea that the domain, the x values, are going to continue on this direction infinitely. And then it goes up, but it also continues to get wider as it goes up. So they also continue in that direction infinitely. So unless we get to problems that have limits on them, like limits of time, that kind of thing, if it's just a straight exponential function, they ask for domain, it's going to be all real numbers every time because it's going to be infinite in both directions. So again, unless it's an exponential growth or decay problem where time is limited, that's what we're going to be looking at. Now, the range values, though, are always limited because there's only going to be one direction that the range can travel. So if you see, again, with this example that I've kind of sketched over here, the y values, the vertical values of this thing, go up forever, but they stop going down as it curves around here at 0. And so this one has a limit line at 0. That's called an asymptote. You don't have to actually know that. You don't have to be able to find what that is. You do have to be able to look at that graph, though, and recognize that, okay, this never drops under 0. 0 is my limit. And so your range is always going to be written as y is either greater than or less than whatever that limit is, depending on which way the graph is headed. So like this graph goes to 0 and never drops under it. So the y values for this graph will always be greater than 0. If I had one that was on the bottom half of this instead, then my y values might be limited to only numbers that are lower than 0. Depends on where the graph is located. And we'll do some practice with that to be able to see it. But it kind of depends on where that's located. We already know an x-intercept is a point on the x-axis. A lot of them don't have one. So sometimes that will not exist. And then a y-intercept, of course, is a point on the y-axis. They're all going to have one of those. And so to be able to identify this stuff, to be able to describe this stuff, we're just going to graph the function in Desmos and evaluate each one from that. So, again, the more you look at these, the easier this gets. But we'll be graphing them and then looking at what those graphs look like in Desmos. So I know it's been a minute since we've used Desmos. That's okay. We'll just kind of go along with it as we go. We'll remember how it works as we go. You also could graph these in the TI-84 and look at them if you prefer to do that in the y equals part of your TI-84. Same difference either way. So we're going to look at some where we graph them in Desmos, and then we are going to describe the y-intercept and then describe the domain and range for each one based on what we see. So if you will, pull Desmos up. Let me go find my Desmos. I'm going to split screen it, I think. I'm actually going to make this small. Oops, somebody's knocking on my door. Hello, hold on. Let me pause what I'm recording.